Usually, like, when we talk about the fundamental laws of physics,
Right.
when we, really crack open the standard model, there is this deeply ingrained expectation of, well, prepackaged precision.
Oh, absolutely.
It's kind of like opening a pristine factory-sealed box of Legos. Like, the instructions are right there on top, the pieces are perfectly color-coded, and the universe essentially points at the little plastic bags and says, here are your particles, here are your forces, here are your symmetries, start building.
Yeah, it's a very comforting way to view reality, certainly.
Right. But we are so used to this that we rarely stop to ask, well, who manufactured the Legos in the first place?
Exactly. In physics, we call those prepackaged pieces primitive gauge groups.
Primitive gauge groups, okay.
Yeah. And the current paradigm, it just simply accepts that the universe arrived for these specific, rigid mathematical structures right out of the factory.
Yep.
I mean, you don't question why an electron has the exact charge it does.
Right, it just does.
Right. Or why the strong nuclear force operates on a specific mathematical symmetry called SU3. You just accept them as axiomatic. They are the undeniable inputs of reality.
Yeah, we really like our building blocks to be distinct. We like them completely categorized from the very first fraction of a second after the Big Bang.
It definitely makes the math easier to swallow.
But, when you step into the world of Philip Lilien's closure spectral field theory, or CSFT, that pristine Lego box just vanishes.
It evaporates.
We are suddenly looking at a foundational landscape that completely rewrites the rulebook. And if you are listening to this deep dive right now, you are going to see how the literal building blocks of everything around you, the atoms in your body, the light hitting your eyes, they don't actually need to be prepackaged at all.
Which is, the absolute definition of paradigm shift. We're replacing that box of independent parts with a single underlying unified rule.
Just one rule.
Just one. It's a framework where you do not start with the pieces. You start with the overarching geometry of the space itself. And the pieces, the forces, the particles, the masses, they emerge entirely on their own as a structural necessity.
Wow.
Yeah, it's a massive compression of how we understand existence. We're moving from a universe of thousands of arbitrary rules to a universe governed by one foundational engine.
Okay, let's unpack this foundational engine then, because obviously before we can build the universe, we have to define the empty space it sits in, right? And the rules governing that space.
Starting point.
So the source material centers on this concept called a closure functional. Now, for those of us who don't, dream in advanced calculus, what exactly are we looking at here? How is a functional different from a regular old function?
That is the perfect place to start. A standard mathematical function is pretty simple. You input a single number and it spits out another number.
Like put in a 2, get a 4.
Exactly. But a functional is a completely different beast. It's a mathematical machine that takes in an entire landscape of possibilities, like an entire configuration of a field sweeping across space and time.
Okay, so it's not just one point, it's looking at the whole picture at once.
Yes, exactly. And it boils that entire complex shape down into a single number, which typically represents the total energy or action of that system.
Okay, so it's evaluating the entire state of things.
Right. And a closure functional is a specific type of variational functional. Because, in physics, systems naturally want to find the path of least resistance.
They want to be lazy.
Exactly. They want to minimize their action. So the closure functional maps out this massive abstract landscape of possible physical states. And its stationary configurations, these are the deep valleys in that landscape where things naturally want to settle, and rest those valleys define what the theory calls admissible sectors.
Admissible sectors, okay.
Yeah, they are the physically allowed states of reality.
I'm picturing this massive rolling landscape of hills and valleys. The functional is the map, and reality is just a boulder rolling around until it finds the absolute lowest, most stable valley to sit in.
That captures the spirit of it perfectly. But the math gets far more elegant than just finding the bottom of the valley.
Because it's physics, of course, it gets more complicated.
Right. To really understand the physics, you have to look at the shape of the valley itself. If you take the second variation of this functional, which mathematicians call the Hessian, you derive something called the closure operator.
The Hessian. Okay, wait. So if the first variation just tells us where the bottom of the valley is, the second variation, the Hessian, tells us about the curvature, right?
Yes.
It tells us if we are sitting in a gentle, wide, shallow bowl, or if we are, trapped at the bottom of a steep, narrow, rocky canyon.
You are touching on the absolute core of the theory right there.
Yeah.
The curvature of that valley determines how hard it is to push the boulder out of it. It defines the stiffness, the the stability.
Oh, wow. Okay.
The spectrum of this closure operator, so all of its possible eigenvalues or resonant states that governs the structural stability of everything in this universe. It links the coupling strength, the localization of the particle, its stiffness, and its sector identity into one single mathematical package.
That's incredible.
It all comes from the curvature of that one foundational operator.
So this completely flips the traditional view. Like, the standard model is the Lego set, where the pieces are pre-molded and completely unchangeable.
Right.
But CSFT, it's more like a massive universal drumhead.
A drumhead, yes.
The pieces, the particles, and the forces, they aren't objects sitting on the drum. They are the natural resonant frequencies emerging from the drum's specific shape and tension. The closure operator is the drum itself.
That is a much more accurate ontology. The spectrum of the operator provides the formal architecture of the resonance. And those distinct notes that emerge, that's what we experience as physics.
But hold on. That doesn't completely make sense. I have to play devil's advocate here for a second.
Go for it.
If every single force and particle comes from this one single operator, this one drumhead, how does it explain the massive, absurd discrepancies in our universe?
You mean the differences in force strengths?
Yeah. I mean, think about gravity versus electromagnetism. Gravity is practically a ghost. A tiny fridge magnet can defeat the entire gravitational pull of the whole Earth.
That's true.
So how can one single drum play a booming, universe-shattering bass note and a microscopic whisper at the exact same time?
That is a brilliant question. And answering it solves what physicists call the hierarchy problem.
Well, the hierarchy problem.
Yeah. Why is gravity so unimaginably weak compared to the other fundamental forces? For decades, the traditional approach, which was heavily championed by string theory, was to argue that gravity is weak because of geometric dilution.
Meaning gravity is leaking out into hidden extra dimensions that we simply can't perceive, like water losing pressure because it's escaping through holes in a pipe.
That was the prevailing hope, yes. But Lilien CSFT says that entire approach is a massive category error.
Wait, really? A category error?
Completely. You do not need to invent 11 hidden dimensions to explain the weakness of gravity. Instead, the theory explains it entirely within the framework of the drumhead, using two concepts: spectral reduction depth and relative closure localization.
Okay, spectral reduction depth. That sounds intense. What does that actually look like physically?
It means we have fundamentally misunderstood gravity's role. Gravity appears weak, not because it is diluted into other dimensions, but because it remains closest to the invariant closure background.
Closest to the background.
Yes. In the language of our spectrum, gravity has the broadest mathematical support across the entire system and the least local concentration.
Okay, I think I follow.
It is not a highly localized sharp peak like a photon or gluon. It is fundamentally a background property.
Oh, wow. Okay, let me try to visualize this for you, the listener. Imagine you're trying to listen to a conversation in a massive enclosed stadium during a championship game. Gravity is the ambient stadium noise. It's everywhere.
Yeah.
It has massive broad support because the entire architecture and everyone in it is contributing to it.
Exactly.
But locally, right in your ear, it just sounds like a generalized low-level hum. It feels weak compared to the person standing 2 inches from you shouting your name.
Yes.
That person shouting is electromagnetism, highly localized, sharp, intense. Gravity is the stadium noise.
And notice what that analogy does. You don't need a hidden magical dimension to explain why the stadium hum is different from a local shout.
Right.
You just need to understand its closure depth, its lack of sharp localization. Gravity isn't a weak force struggling to assert itself in a big universe. It is the baseline geometry of the universe itself, spread perfectly thin. The other forces are sharp, concentrated deviations from that baseline.
That is a genuine ontological reversal. Gravity is the widest, most spread out note on the drum.
Exactly.
But that naturally begs the next question. If the foundational engine is the drum and gravity is just the background hum, how do we get those sharp shouts?
The particle.
Yeah, how do we isolate the specific recognizable notes? The quarks, the electrons, the distinct forces we can actually measure in a particle collider. Because, a generic drumhead struck randomly just produces a chaotic mess of noise.
It does. A generic spectrum from a generic operator would just yield an uninterpretable chaotic soup. It wouldn't form the highly organized universe we inhabit.
Right, it would just be a blur.
Exactly. So to get specific physical architecture out of this noise, CSFT embeds a characteristic polynomial constraint directly into the foundational action.
A characteristic polynomial constraint. Okay, I know what a polynomial is from high school algebra, an equation with variables and exponents, like, x squared plus something.
Right.
But how does an algebraic equation act as a physical constraint on reality?
Think of it as a strict variational penalty. The universe, remember, wants to minimize its action. It wants to find the bottom of the valley.
Yeah.
By embedding this polynomial into the functional, you're essentially creating a mathematical landscape that actively punishes any frequencies that do not fit a very specific, rigid, harmonic structure.
Oh, I see.
It forces the chaotic noise to settle into a clean, highly organized, staged state.
So instead of letting the drum vibrate however it wants, you are clamping down on specific parts of the drum head, forcing it to only play certain perfect harmonics.
Precisely.
And reading the paper, here's where it gets really interesting. This constraint dynamically selects three very specific, familiar-sounding architectures. It forces the emergence of singlet-like, triplet-like, and octet-like sectors.
Yes, what the author calls the Cygnus sector architecture. And it's crucial to understand that Lilien isn't just cherry-picking these numbers to match the standard model.
He didn't just work backwards from what we already know.
No, not at all. The framework interprets this mathematical constraint as a staged progression of physical organization, the staged closure ladder. The math inherently prefers these groupings as levels of emergence.
Okay, let's climb that ladder. How does the math get us from nothing to these specific structures? What is the first rung?
The first rung is level 1, which corresponds to the singlet-like sector. The theory defines this as support persistence.
Support persistence.
Yes, this is the most primitive, basic level of spectral organization. It is simply the foundational persistence of a state, a single, unified, isolated structural identity.
So a singlet is just the baseline assertion of existence, the universe organizing enough to say, I am a distinct thing.
Exactly, just being there.
Okay, what happens when we move up to the second room?
We reach level 2, relational completion, which is the triplet-like sector. At this stage, mere existence isn't enough. Internal relations within the spectral architecture start to stabilize.
Okay.
You have components that must relate to one another to maintain their balance, forming a stable triad.
Wow, that mirrors so much of what we already observe. The three spatial dimensions, or the three types of color charge in quarks, it's the birth of internal structure.
Yes, it builds on itself.
And the final rung on this ladder.
Level 3 is interaction completion, which manifests as the octet-like sector. This is the final ideal stage of the ladder. It represents a fully realized, complex interaction architecture.
The octet.
Right. And again, eightfold structures are deeply embedded in particle physics, such as the eightfold way that describes the organization of mesons and baryons, or the 8 gluons that mediate the strong force.
This is what completely blows my mind. CSFT isn't just inventing 1, 3, and 8 out of thin air. It is deriving them.
It's mathematically inevitable in this framework.
It is saying that if you apply a strict geometric constraint to the background of reality, the universe naturally, mathematically, wants to play a single note, a chord of 3, and a complex harmony of 8.
And to prove this isn't just numerology, the paper dives into some heavy mathematics in its appendices, specifically utilizing spectral projectors.
Spectral projectors?
Yes, denoted as P subs, P sub T, and P sub O for the singlet, triplet, and octet. Without getting bogged down in the equations, these projectors are mathematical operators that isolate the invariant subspaces of the overarching closure operator.
Let me see if I can translate that into something a bit more tangible for you. Think of these spectral projectors like incredibly precise audio equalizers in a high-end recording studio.
Oh, I like that.
You have this massive, overwhelming wall of raw sound coming from the closure operator. The characteristic polynomial constraint acts like the master sound engineer, setting the rules. And the spectral projectors act like the individual EQ dials.
Right.
They perfectly isolate 3 distinct pure tracks from the noise. You push up the first dial, you get the pure singlet track. Push up the next, you get the triplet track. The third isolates the octet track.
That is a phenomenal way to conceptualize it.
Oh.
The minimal polynomial, a core piece of the math, identifies these principal closure levels, these pure tracks you mentioned.
The tracks themselves.
Right. Meanwhile, the characteristic polynomial itself records their multiplicities, essentially, how dominant or loud each track is.
Okay.
The trace identities in the algebra give you the raw multiplicity counts. The ultimate result is a block-structured field theory. The universe has literally sectioned itself off into interacting blocks of 1, 3, and 8.
Okay, so we have our pure tracks. The universe has successfully organized itself into these equalized channels, but this brings up a massive conceptual hurdle.
What's that?
Well, if these tracks, these singlet, triplet, and octet sectors are all existing in the exact same physical universe,
Right.
they have to interact, right? They don't just exist in a vacuum, they mix.
They absolutely mix.
But if they mix, why doesn't the whole system just dissolve back into a muddy soup of chaos? How does the universe keep its bookkeeping straight when these fundamental components are constantly bleeding into one another?
That is the ultimate question of stability. Because you're right, if the system couldn't maintain its boundaries, reality would evaporate.
Right.
CSFT addresses this by establishing two massive pillars of stability: conservation and counting. Let's look at conservation first.
Okay, conservation.
The theory introduces the concept of closure currents, which are derived by varying the action with respect to what is called the closure connection.
Let's define that real quick. A current usually implies a flow of something, like water in a river or electrons in a wire. And a connection, in geometry, usually describes how you move from one point to another while keeping your orientation. What exactly is flowing here, and what is the closure connection doing?
What is flowing is structural identity and charge. These are transport currents. The closure connection is the mathematical rulebook that dictates how information and structural integrity are transported across the different sectors of the field.
Okay, I'm with you.
Now, the crucial rule governing this flow is called the closure-ward identity.
A ward identity? That sounds like a foundational law of physics.
It is deeply foundational. In quantum field theory, ward identities are what guarantee that certain symmetries remain unbroken, ensuring that things like electric charge are perfectly conserved.
Oh, okay.
The closure ward identity states that while the individual sector currents the isolated flows happening strictly within the singlet, triplet, or octet sectors might not be conserved individually because they are constantly transferring and mixing with each other.
Right, they're sloshing around.
Exactly. While those aren't conserved individually, the total closure current across the entire system is exactly covariantly conserved.
Okay, let me bring this back down to earth. This operates exactly like international banking, doesn't it?
International banking, let's hear it.
Imagine the global economy. You have dollars, euros, and yen. Those are our individual sectors, our singlet, triplet, and octet.
Okay.
On any given day, millions of dollars are converted into euros. Euros are converted into yen. If you only look at the dollar current, it looks completely chaotic. It is not conserved. The total amount of dollars is fluctuating wildly as money moves in and out of that specific currency. The paper calls that off-diagonal transport, right?
Yes, the off-diagonal elements of the math represent that mixing between the different sectors.
Right. But if you zoom out and look at the total amount of global capital, the absolute value of all the currencies combined, that total number remains perfectly conserved. The individual currencies fluctuate wildly, but the global bank account is ironclad.
A flawless analogy. The closure ward identity is the universe's global bank account ledger. The total closure current is covariantly conserved.
The global capital of reality.
Exactly. The system can churn, mix, and exchange structural currency internally all at once, but it will never lose its total foundational value.
That is incredibly satisfying. The universe is a perfect accountant. But you mentioned two pillars. Conservation is the first. What is the second?
Counting. Specifically a concept called topological counting. This is detailed in the closure index theorem.
The closure index theorem.
Yes. What Lilien points out here is critical.
Yeah.
We need to distinguish between exact mathematical perfection, which does not exist in a real dynamic universe, and protected physical existence.
Right, because reality is always a little wobbly. It's never as clean as the chalkboard equations imply.
Which is why the closure index theorem is so vital. It is a topological counting law. It proves mathematically that the net topological count of protected, admissible closure sectors is completely invariant under what they call closure-preserving deformation.
Wait, I'm going to push back on this a little bit because counting sounds way too abstract to be a physical shield.
How so?
Well, how does the act of simply counting something make it stable? Like, I can accurately count the apples in my fridge, but in 3 weeks, they are still going to rot into mush. Counting them doesn't preserve their physical integrity.
Because you are thinking of counting like an inventory clerk rather than counting like a topologist.
Okay, fair point.
Topology is the mathematical study of properties that are preserved through deformation. So imagine taking a long piece of string and tying a tight knot right in the middle of it.
Okay, I have a string with a knot.
Now, you can bend that string, you can twist it, you can stretch it out, you can wad it up into a messy ball. In the language of physics, you are subjecting the string to continuous deformation.
Right.
The exact geometric shape of the string is constantly changing, wildly fluctuating, But no matter how much you deform it, stretch it, or twist it, that knot is still fundamentally there.
The knot stays.
Exactly. The topological count of knots is exactly 1. The only possible way to change that count, to destroy the knot, is to physically take a pair of scissors and cut the string, breaking the space itself.
Oh, I see. So the singlet, triplet, and octet sectors aren't just rigid, fragile shapes that can be shattered by a strong breeze. They are topological knots in the closure functional.
Precisely. The theorem highlights a massive difference between raw multiplicity, which is just how many individual things happen to be interacting at a given microsecond, and topological net protection.
Wow.
The paper even distinguishes this topological protection from local variational instability, which is quantified by something called the closure Morse index.
The Morse index, meaning what exactly?
Meaning a system might be locally unstable, it might be wobbling around, shifting energy, vibrating like a plucked guitar string. If you look closely, it looks totally chaotic. But topologically, it is completely protected. This guarantees structural stability under massive deformation. It is the fundamental reason why an electron stays an electron, even when it is being battered by chaotic, high-energy fields inside a star.
An electron is a knot in the closure field. That is genuinely beautiful.
It is elegant, isn't it?
But, you know, everything we have discussed so far, the pure tracks, the perfect knots, the perfectly conserved currents, it all still feels a bit like ideal theory.
In what way?
Well, if you look around, the universe we actually interact with isn't a pristine mathematical chalkboard. It's messy. It's heavy. It is filled with friction. How do we get from this perfect mathematical skeleton to the messy substance we actually observe?
You are hitting on the crucial transition from pure theory to observable reality right there. The exact ideal structure we just discussed is conceptually beautiful, but it is too rigid for physical interpretation in our everyday world. Exact, pure singlet, triplet, and octet sectors do not actually exist in our low-energy reality.
Right, because we don't live in the hyper-energetic, unified birth of the universe. We live in the cooled-down, cluttered, fragmented aftermath.
Exactly. So the theory must generalize these ideal sectors into what the paper calls deformed closure clusters.
Deformed closure clusters.
Yes. In the real world, these frequencies are no longer single, infinitely sharp points of resonance. They have cluster centers, a mean eigenvalue that defines their core identity, and they have internal cluster spreads.
Spread meaning dispersion. Like, the radio station isn't perfectly tuned, it bleeds a little static into the surrounding frequencies.
Yes, they blur, they gain width. And to understand why they blur, we have to look at what is causing the static. This is where Lilien introduces one of the most vital components of the entire theory, the complement.
The complement, capital C, it sounds a little ominous.
It is simply the massive, hidden, suppressed sector of reality that exists outside our visible sigma architecture.
Okay, break that down for me.
Remember earlier when we applied our characteristic polynomial constraint? When we set up our audio equalizers to perfectly isolate the pure singlet, triplet, and octet tracks.
Yeah, we tuned out all the noise.
Right. When we did that, we essentially shoved everything else, all the other messy frequencies of the closure operator, into the background. But that background didn't cease to exist. It is just heavy, dense, and hidden from our direct view.
So if it is hidden, why do we care? How does this invisible complement affect the physical particles we actually see?
Through a deeply established mathematical process detailed in Appendix B called Schur complement reduction.
Schur complement reduction.
Yes. Now, in quantum field theory, when we have heavy, hard-to-observe sectors interacting with lighter visible sectors, we use a technique called integrating out the heavy fields to create an effective low-energy theory, or an EFT.
I need a bridge here. What does integrating out actually mean physically? You can't just delete parts of the universe because the math is hard.
Oh, you aren't deleting them. You are averaging their influence. Think of it structurally. Mathematically, the universe is represented by a giant matrix of interactions. You have a block of the matrix representing our visible, low-energy world, and a huge block representing the massive complement.
Okay, 2 blocks.
Even if you only care about calculating what happens in our visible block, the complement block still exerts influence through the off-diagonal elements, the crosstalk.
Ah, the off-diagonal transport again.
Exactly. Schur complement reduction is the specific linear algebra technique that mathematically folds the effects of that heavy, hidden block directly into our visible block. We calculate the average macroscopic effect of those fast, heavy quantum fluctuations so we don't have to track every single hidden variable.
Okay, so we fold the hidden background into our visible reality. What is the physical result of that mathematical folding?
It derives a dressed sigma sector action, and this leads to the ultimate aha moment of the entire framework: closure dressing.
Closure dress.
The observed masses, the interaction couplings, the transport coefficients of the particles we see in particle accelerators, none of them are fundamental primitive inputs. The mass of a top quark is not a divine, arbitrary constant handed down from on high. It is a dressed quantity.
Meaning it has been modified, weighed down by its environment?
Exactly. The visible sectors make constant, microscopic virtual excursions into the hidden complement.
Virtual excursions.
Yes. Imagine our pure singlet particle. As it travels through space, it is briefly interacting with the dense hidden background, being influenced by it, and then popping back into our visible reality. These virtual excursions generate effective mass shifts.
Wow.
They induce effective intersector mixing, causing particles to interact in ways the pure Bayer theory didn't initially allow, and they generate incredibly complex higher-order interactions.
Let me see if I can paint a picture of this, because it feels like the key to the whole theory. Imagine you are standing at the edge of a massive, freshly plowed field after a torrential rainstorm. It is a sea of thick mud.
Okay, bud.
You, standing on the pavement, have a bare mass. Say you weigh exactly 150 pounds, and you have a specific, pristine, ideal stride when you walk.
I see where this is going. It's a very apt visualization.
But the reality is, you don't get to stay on the pavement. You have to cross the field. The thick mud is the complement. It is heavy, it is everywhere, and it is absolutely unavoidable.
Right.
As you begin to walk, the mud immediately starts sticking to your boots. With every single step, you are making a virtual excursion into the mud, picking up some of that hidden background. By the time you reach the other side of the field, which represents our low-energy observable physics world, you step onto the scale and you weigh 165 pounds.
Your mass has shifted due to the interaction with the background.
Exactly. And because your boots are now incredibly heavy, your pristine gait has completely changed. You are stumbling a bit, your steps are mixing together awkwardly, the mud is the hidden complement, and your new, heavier stumbling state is your dressed reality.
I will say that is genuinely one of the most accurate physical intuitions for sure complement reduction I've encountered.
Glad it works.
The bare you, the 150-pound person with perfect posture, is the exact mathematical skeleton. It is pure, but it is entirely unobservable in the real world because the real world is muddy. The dressed you, covered in mud and stumbling, is the physical substance we actually measure in a laboratory.
The mud is what we measure.
Exactly. The mass of an electron that we measure isn't just the bare knot in the closure field. It is the knot plus the continuous drag interaction with the hidden closure background.
That makes a staggering amount of sense. It completely explains why the standard model has so many weird, arbitrary-seeming numbers for particle masses.
Right, the constants aren't arbitrary at all.
The mass of an electron, a muon, a tau particle, they aren't fundamental rules of the universe. They are just localized records of exactly how much mud stuck to the boots.
And that profound insight is what finally bridges the gap between pure mathematics and experimental physics. We have moved from the high-minded theory to the dirt and mud.
So that brings us to the final phase of our deep dive: phenomenological regimes and the data-facing future.
Yes, looking at the actual data.
We understand conceptually how the mud gets on the boots. But if an experimental scientist is standing at the Large Hadron Collider, looking at petabytes of messy, chaotic collider data, what exactly are they supposed to be looking for to prove that CSFT is actually the correct description of reality?
It's a vital question. How do we test the mud?
Yeah.
We can't just philosophize. We need data.
Right.
Lilien does not leave the experimentalists hanging here. The paper rigorously breaks down a data table of phenomenological regimes, providing a concrete vocabulary for physicists to classify the spectra they are observing.
Okay, let's go through them.
It outlines 4 benchmark effective field theory scenarios, basically ranking how messy the universe has gotten.
Let's walk through them, starting from the cleanest. Scenario 1 is weak dressing.
In the weak dressing regime, the complement-mediated corrections, the mathematical mud, are perturbatively small. Internal splitting within the clusters is minimal, and the intersector mixing is barely noticeable. It's a very clean, almost ideal state.
To keep our analogy going, you walked through the field, but had mostly dried out. You got a little dust on your shoes, but the original singlet, triplet, and octet structures are incredibly obvious. You can look at the data and clearly see the perfect tracks.
Precisely. It is the easiest regime to interpret. But as energy scales shift, we move to scenario 2, moderate dressing.
Moderate dressing?
Here, we start to see very visible, measurable shifts. The couplings and the masses are noticeably altered from their bare theoretical values. However, the cluster centers, the core identities of the sectors remain completely identifiable.
You've got actual mud on your boots now. You are measurably heavier, and your stride is a bit labored, but if I look at you from across the field, I can still easily tell it's you. The core identity of the particle is preserved.
Exactly. Identity is intact.
Scenario 3, however, sounds far more intense. Resonant mixing.
It is where the analysis gets extremely difficult. In resonant mixing, the intersector mixing the aggressive crosstalk between the singlet, triplet, and octet sectors becomes mathematically comparable to the protecting spectral gap itself. Hybridization begins to dominate the system.
Hybridization, meaning the pure tracks are violently bleeding into each other.
Yes.
The mud is so thick and the ground is so slippery that you are constantly crashing into the people walking next to you, exchanging mud, to the point where, from a distance, you all look like one tangled, stumbling entity. The mixing is so strong it actively challenges the observer's ability to separate the sectors.
Exactly. The particles are hybridizing their identities through their shared interaction with the complement. And finally, we reach the most extreme environment, scenario 4, strong anisotropic splitting.
Anisotropic meaning it's breaking symmetry. It's not uniform anymore.
Correct. Here, the internal cluster deformation becomes so extreme that it absolutely dominates over the broader closure ancestry. The cluster spreads out massively, breaking its symmetry severely.
Wow.
It becomes incredibly hard to see the original sigma structure. It's as if you are carrying so much mud and slipping so wildly that someone observing you might not even realize you are a human walking. They just see a chaotic, asymmetric mass of earth moving across the field.
That's intense.
But the vital takeaway is this. Even in this chaotic state, the underlying topological knot, the mathematical ancestry, is still fundamentally there. The string has not been cut.
So these 4 regimes give physicists a practical roadmap, a way to look at the incredibly confusing, messy data from particle smashers and say, look at this weird, unexpected mass shift. We don't need to invent a brand new magical particle to explain it. It is simply a known triplet sector currently undergoing moderate dressing from the background.
That is the ultimate call to action for the entire field of physics that this paper lays out. For decades, the field has been obsessed with searching for isolated particle anomalies, smashing things together and hoping a shiny new Lego piece pops out of the debris.
Right, hoping for a surprise.
Lilien is arguing that this is the wrong approach entirely. Physicists need to stop looking for new pieces and start looking for clustered spectral organization. They should be analyzing the data for correlated mass and coupling shifts that are governed by a common hidden stiffness scale.
Stop looking for new pre-molded Legos and start listening for the underlying resonant frequencies of the drum.
Yes. Look for the structural echoes of the closure operator. Now, the paper is rigorously honest. It notes that there are still massive open tasks.
Right. This isn't the end of physics.
Far from it. This is a foundational framework, not the final, completed theory of absolutely everything wrapped in a neat bow. The author explicitly lists several critical frontiers for future development.
What's at the top of the to-do list?
For one, developing a first-order realization of the closure Dirac-like operator.
Meaning what, in plain English?
The Dirac operator in standard physics is what brilliantly describes fermions, like electrons, and incorporates spin. CSFT needs to sharpen the math to show exactly how a Dirac-like mathematical structure natively emerges from the purely bosonic closure landscape we've been discussing.
Oh, okay. That makes sense.
They also need to sharpen the index density, basically expanding the mathematical rigor and local application of those topological counting laws we talked about earlier.
The knots.
Right. But the absolute biggest frontier, the one the paper explicitly flags as the ultimate test, is extending this entire classical framework to quantum structures.
Oh, because everything we've talked about today, the drumhead, the pure tracks, the mud, has essentially been classical, or at best semi-classical physics.
Right. It is a masterpiece of macroscopic structural organization. But reality, at its deepest, most microscopic level, is quantum mechanical. The theory must eventually prove that things like the closure ward Takahashi identities, the quantum versions of our banking conservation laws, hold up when the universe is fluctuating with quantum uncertainty. Bringing this fully into the quantum realm is the next great leap for CSFT.
Wow, okay. We have covered a truly staggering amount of ground today, and we've completely dismantled the standard view of reality in the process. Let's try to bring it all together.
It's a lot to process for sure.
We started by abandoning the gauge-first ontology, the comfortable, historic idea that the universe simply came with a factory-sealed box of preset Lego pieces.
Out with the Legos.
Right. Instead, we embraced a closure-first ontology. We saw how a single, beautifully unified mathematical object, the closure functional, acts as the foundational engine of reality.
We examined the geometry of that engine, discovering how the Hessian creates the closure operator.
And through that, we realized that the hierarchy problem, the baffling weakness of gravity, isn't about gravity leaking into sci-fi extra dimensions.
Not at all.
It is about spectral reduction depth. Gravity is the baseline, spread-out hum of the universal drum. Everything else is a sharp, localized note.
From there, we climbed the staged closure ladder. We watched how a strict characteristic polynomial constraint forces the chaotic noise of the universe to organize perfectly into singlet, triplet, and octet sectors, our pure, equalized tracks of existence, mirroring the fundamental forces and particles we know.
We verified the pillars of stability, learning that while individual local accounts might fluctuate wildly, the universe's total closure current is covariantly conserved.
And we discovered that fundamental particles survive the chaos of reality because they are protected like topological knots in a string.
Finally, we confronted the messy, empirical reality. We learned that the universe we observe every single day is a dressed universe.
A muddy field.
Exactly. The arbitrary masses and forces we measure in laboratories are simply the effective physical results of our ideal mathematical structures dragging through the dense, heavy, hidden complement.
It is a framework that completely unifies ontology, dynamics, and phenomenology. It takes a universe of thousands of disjointed, arbitrary rules and parameters and condenses it into the elegant vibration of a single geometric constraint.
It is breathtaking. But as we wrap up this deep dive, I want to leave you, the listener, with one final thought, something to mull over the next time you look up at the stars or even just look at your own hands. We mentioned that the quantum extension is the next great frontier for this theory. If the classical universe we've discussed today, its unyielding forces, its heavy masses, its rigid structures, is really just the low-energy, dressed illusion of a deeper hidden closure spectrum, what happens when we apply this to the bizarre realm of quantum mechanics?
That's the million-dollar question.
In the quantum world, the act of observation itself changes the outcome. So if reality is just the macroscopic echo of a mathematical constraint, a forced vibration on a universal drumhead, what is doing the constraining? Who or what is tuning the drum?
That's a thought to keep you up at night.
Next time you interact with the physical world around you, ask yourself, are you actually seeing the fundamental universe? Or are you just seeing the mud on the boots? Are you seeing reality, or were you just seeing the dressing? Thanks for joining us on this deep dive. We'll catch you next time.